Hey, chemistry. We're here today to talk about some of the deeper details behind the the science that goes into the last two labs that we've done. We've done the flame test and we've done the silver nitrate test. This video is going to talk about sort of the nitty-gritty that is making the flame test work the way it does. So you might remember we had some cool flames. We put chemicals in flames and they made colors. My favorite was always the copper. You can see on the left hand side the green flame, which is really unique and kind of beautiful. But on the right side there, you can see the actual individual colors that flame is made out of. You can see the green and also the yellow and the blue and a little bit of purple mixed in there. You wouldn't know it, but those colors, those wavelengths of light are all mixed into that green flame. Something like strontium has a more complicated set of spectrums or spectra, as the plural should be. And this is what we can use for something called spectroscopy, looking at the spectra of light that are produced by different sources to analyze and understand them. And you can kind of maybe see where these are connected. You got a lot of the red colors over there that kind of wash out the lighter wavelengths of blue and green and yellow that are present in there. And so we see strontium flame as red. But let's get into more detail about how we see these and where these lines are produced. These aren't magic lines. These aren't made using some complicated computer program. These are pretty straightforward. Some of you, if you're into classic rock or have parents or uncles or anybody who's into classic rock, you might be familiar with Pink Floyd, right? They've got their famous Dark Side of the Moon album with the prism on it. And so you might be familiar with the idea that you can put white light into a prism and then split it into its different colors. That is fundamental at the heart of spectroscopy. Now, if we take a look at what actually happens through a prism, as it gets bent, as the light bends through, the different wavelengths of light bend different amounts, and so then they get spread out. The red gets separated from the orange and the yellow, and so on. Now, imagine that you're looking at a green flame. If only the green and the yellow and a little bit of blue are mixed in there, then you're only going to see those specific colors coming through. And if they're very distinct, then they come through in those very particular lines. And that's what spectroscopy uses. Now, to give a more in detail example, you should know that we can also use gases for this. All of your neon lights, for example, are used by running electricity through a gas. Helium produces a pink light, and this would be the spectrum that it has. Neon, you're familiar with neon signs, has a distinctive red-orange color, and this is the spectra of neon gas. And you can see where all that red comes from. Now, you can also get mercury lights. These are brighter, bluer kind of lights. Maybe you've seen them outside of garages or in really brightly lit parking lots. You get that mercury light. That actually comes from these spectrums. But the most simple gas of all is hydrogen. Hydrogen consists of one proton and one electron, and so it's a very simple spectrum. It's got one red line, one teal line, and two purple lines. If hydrogen only has one electron and one proton, where do these multiple lines come from? We're going to get into that. That's one of the most interesting things we're going to talk about because it ties back to electron configuration. You might remember the different energy levels that we've got, and it turns out they are different distances. The first energy level is very close. The second energy is much further than third and fourth, and so on. So we've got that one electron that always hangs out at the first energy level for hydrogen. You know that because hydrogen's electron configuration is 1s1. However, here's the cool thing. If you put a bunch of energy in to an atom, sometimes those electrons get all hyped up. They get what is called excited, and they might jump up. Maybe an electron will jump up to the second energy level. And just like a kid on a sugar rush or a mosquito chugging Red Bull, that energy rush cannot last. Eventually, it's going to crash back down. So let's say, for instance, that it gets put all the way up to the third energy level and then falls back down to the second. in the details of things. We know that energy is never actually lost. It's never destroyed. It always just changes forms. We put the energy in, maybe in the form of flame or electricity, and it has to come out in some way. The way that it comes out when energy is released from electrons that fall back down is as light. When an electron in a hydrogen atom falls from the third level to a second level, it produces a single photon with a red wavelength. It produces a single photon of red light. And depending on how much energy goes in and then comes out of these electrons, it can produce different kinds of light. For example, if we go from 4 down to 2, that's where we get a sort of a blue-green or a teal photon. If we go from 2 down to 1, we actually produce a lot of energy. That's ultraviolet light. That's extremely high energy. We could take a look at the nitty-gritty math behind this. Scientists study the details of this math, and this is part of how we understand how much energy is in these different energy levels, is by analyzing the light produced by different atoms. We're not going to get into the math here. You don't need to do these calculations, but I just want to show you that this is how we know what these electrons look like. We can't look at the electrons themselves, but if we study how they behave and what kind of light they produce when we give them certain amounts of energy, then we can learn about them. And so if we go from 3 to 2, we produce a red photon. If we go from 4 to 2, we produce that teal photon. Turns out the drop from 5 to 2 is what produces the one purple line, and from 6 to 2 is what produces the other. We also end up producing some ultraviolet light when it falls from 2 back to the very first energy shell. And from 4 to 3, it turns out there is a little bit of infrared light that's produced. All of this light comes from just excited hydrogen atoms. And that's where these lines come from, because we've split the light from those excited hydrogen atoms into the rainbow, but the only pieces of the rainbow that are there are just these few lines, the red, the blue, and the purple ones. So this is exactly what happens when we burn a copper flame. We take that rainbow, that part of the rainbow that's present in the green flame, and we split it up and we could see. And this is how, even if you were colorblind, if you totally couldn't tell the difference between red and green, if you had a spectroscope, you'd be able to analyze the exact lines, you could measure them where they are and say, I can tell green from red because I can look at the wavelengths. That is pretty cool, and that is spectroscopy.